video, we're going to discuss Gauss-Jordan elimination. We say that a matrix is in RREF, or reduced row echelon form, if the following four criteria are met. We need the first non-zero entry in each row of the matrix to be a 1. We need these leading ones to have zeros everywhere else in their columns. We also need these leading ones to move down and to the right. And finally, we need any zero rows to be located at the bottom of the matrix. So let's get a feel for RREF, or reduced row echelon form, by looking at some matrices that are in RREF. So in this section, we'll often be dealing with augmented matrices, meaning we'll have the coefficients over on the left, then we'll have a vertical bar, and we'll have some constants over on the right. But when talking about RREF, we are only looking to the left of the vertical bar. So the most typical example of a matrix that is in RREF is when the left side here looks like the identity matrix. So let's just circle the first non-zero entry that we see in each row. So in the first row, it's the first entry, second row, it's the second entry, and in the third row, the first non-zero entry that we see is in this third position here. So our first non-zero entries in each row are 1s. These leading ones, they do have zeros everywhere else in their columns. The leading ones do move down into the right. And there aren't any zero rows in this matrix, so we don't need to worry about the fourth criterion here. Some other examples. Okay, something like this would be in RREF. The first non-zero entry in the first row is here. The first non-zero entry in the second row is here, and the third row is a 0 row. So our first non-zero entries are 1s. These leading ones have zeros everywhere else in their columns, and the leading ones do move down into the right. So what we're saying here is that as we scan down the matrix, the leading ones have to be further to the right than in the previous row. The leading ones are not necessarily always going to go straight down the diagonal, but it's just that as we're reading down, leading ones will move further over to the right. Okay, and our 0 row is located at the bottom of the matrix. A couple more examples of matrices in RREF. We could have something like this. So our first non-zero entries in our first 2 rows are there. We've got a 0 row at the bottom. So our first non-zero entries are 1s. There are zeros everywhere else in their columns. The leading ones do move down into the right, and our 0 rows at the bottom of the matrix. So that all looks good. Another example, we could have something like this. Maybe a couple 0 rows in this matrix. So our first row, the first non-zero entry that we run into here is the 1. So yes, we do have a leading 1 in each of our non-zero rows. The leading one does have zeros everywhere else in its column. We don't really need to worry about criteria 3 because there's only a single leading 1 in this matrix. And yes, any 0 rows we have are at the bottom of the matrix. So as we go through our examples of Gauss-Jordan elimination, it will be important to be able to quickly recognize when a matrix is in RREF, and this gives us a good overview of what we'll be looking for. A typical problem in this section will ask us to solve a system using Gauss-Jordan elimination. The first step will be to write up our system as an augmented matrix. So we're going to enter our coefficients on the left side, and on the right side we will enter our constants. So it can be helpful just to label the columns X, Y, and Z here. That way we can match up the coefficients with the right variable. Over on the right side, we're just entering the numbers. So the first equation would be translated as 2, 1, 3, so 2x plus y plus 3z is equal to 24. And we can do the same thing for each of our equations here. In the second row, there are no x's, so we should really write 0, 3, 4, and then 36. And for the third row, 1, 1, 1, and 11. Now, when the question says solve using Gauss-Jordan elimination, what that's asking us to do is to get the left side of this matrix into reduced row echelon form. So into RREF using the row operations that we have developed earlier. These are the same row operations that we used when we were finding the inverse of matrices. So first thing we'd like to do is get a 1 in the upper left-hand corner. Easiest way to do that, let's switch row 1 and row 3. So top row becomes 1, 1, 1, 11. Bottom row becomes 2, 1, 3, 24. Middle row will not be changing. All right, so we've got our 1 here. We can now use that 1 to get zeros in the rest of that first column. So what we really need to fix here is the 2. To eliminate a 2, we're going to write down the row that we're on, so row 3. And because it's a 2 here, we're going to go minus 2 times our pivot row. Pivot row, just the row that contains that leading 1 that we created earlier. So doing row 3 minus 2 row 1, we're going to get 0, negative 1, 1, and over on the right side, 24 minus 22 will give us 2. Our top 2 rows will not be changing, so we'll just recopy those. And that's our first column all sorted out. So now we are going to move down into the right, and we would now like to create a 1 in this position here. So let's take row 2 and divide it by 3. We'll get 0, 1, 4/3, and 12. We can circle this. This is going to be our pivot to help us work on that second column. Our top and bottom rows will not be changing, so we can recopy those. Okay, and now we're all set to continue working on the second column here. So we would now like to create zeros in the rest of that second column. So let's deal with this 1 that we've got in the first row. To eliminate that, we're going to go the row that we're on minus 1 times our pivot row. So row 1 minus row 2. To get rid of this negative 1 in our third row, let's go the row that we're on, and because we're eliminating a negative 1, we're going to go plus 1 times our pivot row. So the multiple of your pivot row that you're using is just the negative version of the number that you're trying to eliminate. If you're trying to eliminate a 1, we're going to go minus 1 times our pivot row. If we're trying to eliminate a minus 1, we're going to go plus 1 times our pivot row. So general procedure to create zeros is just the row that we're on plus or minus an appropriate multiple of our pivot row. All right, well, let's do the calculation here. Row 1 minus row 2 is going to give us 1, 0, and then we'll have to do 1 minus 4/3. So let's think of this as 3/3 minus 4/3 will give us minus 1/3. It's good practice with our fractions. And 11 minus 12 will give us negative 1. Middle row is going to stay the same. And then down in the bottom row, we're going to add row 3 and row 2. So we'll get 0, 0, Over in our third column, we'll have 1 plus 4/3. So let's think of this as 3/3 plus 4/3 would give us 7/3. And over on the right side, 14. We've got the second column all figured out. Our leading one was in this position, so we're now going to move down and to the right, and we're going to get a 1 in this bottom right-hand corner. To do that, let's take row 3 times 3/7, and that will give us a 1 in that position. So we'll have 0, 0, 1. And if we'd like, we can do a little bit of calculation underneath the matrix. We're going to have to take 14 times 3/7. So we can factor out a factor of 7 from the numerator and the denominator, and that will give us a 6. So we're getting a 6 over on that right-hand side there. Again, circle our leading one there for the third row. So very last thing we have to do to get this left-hand side into RREF is just fix up the rest of this third column. We're going to need to get rid of these 2 entries that are sitting above our 1 there. So to do that, let's take row 1 plus 1/3 times our pivot row. That will get rid of our minus 1/3. And to get rid of our 4/3, let's go row 2 minus 4/3 times our pivot row. All right, so starting with our first row, row 1 plus 1/3 times row 3 is going to give us 1, 0, 0. And over on the right side, we're going to have a minus 1 plus 1/3 times 6. So if we factor out factor of 3 from our numerator and our denominator there, this is looking like minus 1 plus 2. So that gives us a 1 in that position there. Moving on to our second row, if we do row 2 minus 4/3 row 3, we get 0, 1, 0. Again, we can do a little bit of calculation on the side here. We're supposed to be doing 12 minus 4/3 times 6. So let's cancel out a factor of 3 from the numerator and the denominator there. We've got 12 minus 8, so that looks like 4. To confirm that we've created reduced row echelon form on the left side, might help to circle our first non-zero entry in each row. So yep, our first non-zero entries, they're all 1s. We do have 0s everywhere else in the columns of those leading ones. The leading ones are moving down and to the right, and we don't have any 0 rows in this matrix, so we don't have to worry about that. So once we've reached the reduced row echelon form, that's how we know that the problem is done, and now it's just a matter of writing down our solution. So if we think back to the setup of this matrix, remember that our columns represented x, y, and z, and over on the right side, this last column just represented the number. So if we look at this first row then, what that first row is really saying as an equation is that 1 times x plus 0 times y plus 0 times z is equal to 1. In other words, if we write this a little bit more briefly, it's just telling us x is equal to 1. The second row of this matrix here, really translated as an equation, would say 1 times y is equal to 4. So in other words, y is equal to 4. And our bottom equation, that's telling us 1 times z is equal to 6. So in other words, z is equal to 6. So what we're getting is the solution, if we write it as an ordered triple, looks like 1, 4, 6. And we could go back to our original equation, check these values in our first equation, in our second equation, in our third equation, and that will convince us that we have indeed found a solution to the system.